The video we're going to look at today um, examines our journey, or begins our journey, I guess, down through the techniques of integration. Now, these will be an important set of skills for you to acquire as you continue with your study of calculus. Um, the first strategy that we're going to examine is what is referred to as the substitution technique. Now, having said this, I'm going to show you this method and how it works. Having said that, many of the examples that I may do, you you will look at and say, well, I really didn't need to do a substitution. I could have figured that out just by looking at it by what I will call inspection. So don't feel you have to use this method. Now, there are certain examples where, yeah, you're pretty much going to have to use this strategy. However, many examples you will be able to do by inspection. And I'll kind of show you what I mean by that in the beginning here, because we've actually been doing the substitution technique. We just haven't been calling it that when we did antiderivatives, which again was quite a while ago now for you folks. So certainly we may be able to practice with that, and we'll have to get brushed up on that over the next week or two. All right, so we're going to do this by starting with examples. So let's suppose we had the example here in front of us, and we were trying to get this integral. Well, if we looked at it prior to me saying we were going to do any kind of new integration techniques, I think most of you would have been able to do this question by looking here and saying I have u to an exponent with du sitting next to it. Now we know that du should be 2x, but we're actually here getting 3x. Um, what we did earlier on is we did it with antiderivatives. Of course, we didn't have this symbol there, but here's what I would now suggest we could do. We could just put our integral sign there, take this constant, pull it out to the front, get it out of the way. I'm just going to change the order of these a little bit. X squared plus 1 to the 20th. I'm going to put my x here and my dx here. And we know that if we have u to some exponent times du, the antiderivative is the undoing of a chain rule. If you can remember from a while back, that was 1 over n plus 1 multiplied by u to the n plus 1. Basically add one to the exponent and divide by the new exponent. So if I look here, if this is u to the n, du would be 2x. I just have x. Problem solved. Like we talked about earlier when we did this, you can't just insert a constant here without doing something to offset that constant so you don't change the value of the initial integral that you were dealing with. So if I put a 2 there, what we did earlier is if I put a half here, what we're going to do now is any constants that we insert into these, we're now going to deal with just out in front of our integration symbol. So this would become 3 over 2. So my solution will now be 3 over 2, add 1 to the exponent, so it's going to be 21, divide by that new exponent, 1 over 21, and then I'll have u to the n plus 1, and then of course for indefinite, meaning there's no bounds on these, we always are going to put our plus c back on here now. We just tidy that up a little bit. 3 goes into 21 7 times, so it'll be 1/14 x squared plus 1 to the exponent 21 plus c. And that's what we would have done when we did with antiderivatives. When we were doing antiderivatives, the only difference really is we weren't using the integration symbol at that point. I haven't filled you in on what that notation actually meant, but we're now kind of starting to understand that this symbol is just a symbol in math that leads us to take the antiderivative. And now what I'm going to show you is how you would do that same question using this substitution technique that I refer to up here. And the way it works, obviously it's going to have something to do with the substitution. We're going to choose something in the original integral, and we're going to switch this integral to a new set of variables. So rather than having x's in here, we're going to have, generally the variable of choice is a u, but it really doesn't matter what letter you choose, but commonly it's going to be a u. So for example, I'm going to look here, I have that original question. There's no easy way to tell you what to let u equal. There's no magic. There's, oh, you always let u equal this, you always let u equal that. It comes with experience and practice. kind of as a rule of thumb, you're going to want to let u equal something so that when you find its derivative, that part of, or at least the variable part of the derivative shows up in there. For example, I'm going to let here u equal x squared plus 1. Now, the reason I'm going to do that is because of what I'm going to do next. The next thing what I'm going to do is I'm going to take the derivative of the letter u with respect to the letter x. Well, that would mean in notation du over dx equals, I'm going to take the derivative of the right side with respect to x. That will be 2x. Well, I'm going to just rearrange this a little bit and isolate and get du by itself. So I'm going to multiply both sides here by dx. So du is equal to 2x dx. So I've got all of this information here now. And now just to backtrack for a second, sometimes people say, well, why didn't you let u equal this? Why didn't you let u equal x squared plus 1 to the 20th? Well, the problem would be if that was what I let u equal, when I went to go to do my du would be 20 times that to the 19 times 2x. But then that's going to be much more complicated, and that's not showing up elsewhere in here. So that's not a great choice for my u substitution. And with these in the beginning, you may find that sometimes you choose some option. You say, I'm going to let u equal this. And you start down through, then you say, oh my goodness, this is going nowhere in a hurry. And you kind of have to turn the pencil over, erase it, and start again. And that's completely normal with integration. It's not something that you're instantly going to get correct the first time, every time. Even I've been doing these for many, many years. Still, if I was throwing an integral I hadn't seen before, I might try something and say, this isn't going very well. Erase it, and I say, oh, I'm going to try this instead now. So it's very much like a problem solving. There's no words here. These are little problems that we're going to have to solve and figure out a strategy that will help us. Okay, so now to go back, so well, that's great. What are you going to do with all this mess you got here now? So here's the goal of this. The goal of this is to rebuild this question so that instead of having x's, it's going to have u's in the integral instead, the letter u. I'll backtrack in this one as well. If you're doing a substitution technique, one substitution you would never ever do is let u equal x, because all that does is give you the exact same question with the letter switch from an x to a u. So in the substitution technique, letting u equal x will never be of any value to you. Now, if I go over here and say, okay, I'm going to rebuild this question. Well, I've got this, which is u. So this is u to the 20th. I've got x dx. I'm close to x. I have 2x dx. So maybe I'll just do this. du over 2. So du over 2 would equal x dx. I'm going to take the question now. This 3, I'm just going to get it out of the way to the front. I'm just trying to get rid of the x's and turn them into something in terms of u now instead. Instead of x dx, so if I kind of looked at these two grouped together, x dx, I can put in du over 2. Now du, of course, always goes out at the end. Don't stick it in the front of your integral. Always the last thing on an integration. Over 2, well, I'm going to put the over 2 part out there. This is all going to be multiplied together. So whether the 2 as the denominators here or out here makes no difference. Then, what else do we have here? So then we've got this to the 20th. So now I've got u to the 20th. So this original question has now been converted into this new question involving just the letter u. And this now just becomes undoing a power rule. So it's 3 over 2. Any variable to an exponent, to do its antiderivative, you add 1 to the exponent and divide by the new exponent. 1 over 21. 1 over 21. 1 over 21 u to the exponent 21. I'm going to put my plus c back in here. Same as now 3 was in 21 7 times, multiplied by 2 is 1/14. And then what you do is you switch back to the original variables. There's no u's anywhere to be found in here, so your answer can't have the letter u in it. That wouldn't make sense for an integral that had a bunch of x's in it. So now I just replace this letter U right here with what U equals. You look over here and say, what is U? U is this right here. U is equal to x squared plus 1. So now I'm going to replace this back with the original variable, x squared plus 1 to the 21 plus c. Now look at what I got over here. Same answer. And I know some of you are saying, why in the world would you ever get into all of this when I could have just done this over here? I agree 100%. You're going to find next year, though, many students you may run into won't have as much experience doing integrals as you folks may have. They may not be as competent in differentiation rules as you folks hope they're going to be, and they're going to have to rely on this strategy. This is only something you're going to move toward if you can't see a way to get through it just by inspection. Then you're going to look at switching out to new variables. So as I said earlier, some of these ones that I'm going to do, you're going to look at and say, well, I wouldn't have done it that way. I would have just left the x's in there and did this. Absolutely fine, and that would be great. All right, on to our next example. Now, this one, when I look it over, so I see sine squared x and cos x. Now you got to know your differentiation rules here. I do know that the derivative of sine is cosine, and I know the derivative of cosine is negative sine. We could do this one easy enough by just saying, I've got sine x squared with a cos x sitting right beside it. And I think you would agree that's the pattern of a chain rule. I've got u to an exponent, and sitting right next to it is du. We can easily undo this without doing a substitution and say the answer is 1/3, add 1 to the exponents, and that would become sine cubed x plus c. That's how we did antiderivatives back in one of the earlier units in the course. Easy, look at that, 2 lines done. Having said that, I'm going to use this as an example just to show you how substitution would work. So all of a sudden someone gets here and they say, oh, okay, I'm going to let u equal sine of x. I find in the beginning sometimes students will say, I'm going to let u equal sine squared x. Well, the problem with doing that is if u is sine squared x, to get du, which you're always going to need to find du because that's the only way you're going to generate a dx. And you're going to need something to put in there for dx. So whatever you let u equal, the next thing you're always going to do is take the derivative of it. And if u is sine squared, to take its derivative, you're going to have to use a chain rule. And that's going to make a more complicated expression down here. All right, so having said that, what I'm going to do is take du now of this. Now, it's du over dx, and the derivative of sine x is cos x. Derivative of x would just be 1. What we eventually start doing is, because what we're always going to do next, we're always trying to solve for dx. So we're always, because this dx is always going to be generated in the denominator of your u here after you do its derivative, which will always lead you to multiply both sides by dx. So probably from this point forward, I'm just going to start automatically writing the dx over there. And again, I've showed you in a couple of examples here why, but it's just to save us doing this step every single time. So now du is cos x dx. Well, if I look over here and say, well, could I rebuild this question? U is sine x, so this is u squared, cos x dx, cos x dx. I could put a du in its place. So the original question would become u squared du. Now just integrate this question in terms of u rather than x. So it's going to be u cubed over 3 plus c. And then you switch from u back to whatever u equals. U is taking the place of sine x. So this now becomes sine cubed x over 3 plus c. Same thing I got over there. Be careful here as well, just to remind you, there's a difference between sine cubed x is not the same thing as putting the cubed on there. That's cubing the argument. This one means to cube the whole thing, which is what we intended it to mean. This one means just the x is getting cubed, the argument. All right, so when I put that exponent there, Don't let it carelessly drift over here because that'll be incorrect. All right, so there's two pretty basic examples that we probably would not have relied on a substitution method to get the antiderivative or the integral for, just because of our experience doing these earlier on with antiderivatives. Okay, I got one more here. All right, so this one, if I look at it, now it may be not as obvious what we're going to let u equal here. The good news is I have the fortune of a lot of experience doing these types of questions. So I can kind of see the pattern, which hopefully you folks will get to that point as well. I'm going to let u equal just the square root of x. And again, sometimes people say, why don't you let it be e to the square root x? Well, the problem with letting it be e to the u is the derivative is e to the u times du, which is going to be kind of a complicated mess, which I don't have extra down here to resubstitute. I'm trying to get stuff here that will basically take the place of all this stuff that I currently have. Let's take a look at du. So du, remember it's du over dx. I'm just going to cheat it a little bit. Take the derivative of this, 1/2 x to the negative a half, and that dx that would have started here. I'm just going to now write it over here. Great. Well, now let's see if I can mold this into what I've got over here. X to the negative 1/2, and I got a 2 down there. So if I took the 2 to the other side, that, remember, it's a puzzle. You're trying to turn this stuff into this with u's instead of x's. X to the negative a half could be written as 1 over square root x. Half means square root, negative means in the denominator. Well, I've got dx, a 1 over root x. That's that. Well, 2 du could take that, the place of that. And then I've got e to the root x, and root x could be replaced with the letter u. So this question could be rebuilt, be this new integral. So now it could be the integral of, constants are going to go up front. The du is going at the end. There's your 1 over root x dx taken care of. 1 over root x dx, 2 du, and then e to the u. And now hopefully our differentiation rules will start to slowly come back to us. The derivative of e to the u is e to the u du. So the antiderivative of e to the u du is e to the u. Don't forget our plus c. Switch back to the x's. And now that would become root x plus c. And there's my substitution, and there's my answer to that integral. All right, so hopefully those three examples kind of get you going with how this whole substitution strategy works. We're now going to progress along our examples here. Okay. This one's going to be a little different. It's not going to be as obvious as the first three that we did, where if I let u equal this to du, it all kind of fell together very nicely in those first three examples. Let's take a look here. If I look at, let's suppose I'm going to make an incorrect substitution just to show you what will happen. So you'll say, well, this isn't going in the right direction, because I'm telling you right now, as you start doing these in terms of practice, you're going to let u equal the wrong thing sometimes. So let's suppose I came here and said, I'm going to let u equal x squared. Well, then du will be 2x dx. Now I got to look at this, and I got to somehow use this to rebuild this question. So I'm going to put u in there. Now for dx, here's the problem with getting the dx is du over 2 could be x dx. I don't have x dx. I could up here say, well, the square root of u would be equal to x if I took the square root of both sides. So then if I go to rebuild this, let me see what I've got here. think of, instead of x squared, I can have maybe x square root x minus 1 dx. So if I went x dx, x dx, x dx, that's du over 2. And then I've got still an x left, so that's still a root u left. And then underneath here, I'd have the square root of u to the half minus 1. That didn't look to help my cause a whole lot, did it? So at that point, I'd probably say, nah, I'm not sure about that substitution. It didn't go well. Start over. Take your erase. Don't want to do these in pen. Do them with a pencil. Well, say, well, that didn't go so well. Let's try something else. Remember, u equals x is never an option. Doesn't help anything. Just switches the letters. I'm going to go here with x minus 1. Now, again, you may say, why don't you go with square root x minus 1? As I said earlier, whatever I let u equal, the next thing I'm doing is taking the derivative of it. Well, if u is the square root of x minus 1, du is going to involve the chain rule, and you're going to get quite a mess here, which is usually not going to help you with a substitution. By letting u equal this, du equals, well, the derivative of x is just a 1. Now, this is not bad, because what you can do is you can rearrange this to get what x equals. So x would equal u plus 1. So then I can look at this integral and say, all right, I've got x, which is u plus 1, squared. The square root of x minus 1. Well, x minus 1 is u, so this would be the square root of u. And then dx just gets switched out for du. Well, this is better than the problem with what I had here before was I can't use any kind of a shortcut to expand this out. This isn't the derivative of what's underneath here, so it's not a chain rule. We were stuck. There was nothing I could do. The substitution was absolutely necessary here. There's no way around it. Now, sometimes students will get here and say, geez, I don't know. This doesn't look much better. But if you just bear with me and watch what will happen here. Square this binomial. So u squared plus 2u plus 1. Switch this out to u to the half rather than square root of u times du. Because the reason I'm doing this is my goal is to try and end up with a bunch of terms added and subtracted that are just u to some exponent. I don't care if they're fractions or decimals, doesn't make any difference. As long as it's a variable to a number, we can always just add one to the exponent and divide by the new exponent. Well, if you look at where we are at now, if I just took this and multiplied it back into here, I'm going to get u to the 2 multiplied by u to the half. Well, when you multiply, you add exponents. So this is going to become u to the, this is 2 over 1, which should be 4 over 2. Add that, it's u to the 5 halves. Plus 2u, so 1, which is 2 over 2, plus 1 over 2, u to the 3 halves. And then 1 times u to the half is u to the 1 half. du. I reached where I said I'd like to get. I'd like to get just a variable to an exponent. Variable to an exponent. There's no exponents out here. There's no radicals. We just have 3 power rules to undo now. And here would be our final answer. So if I add 1 to 5 halves, that's going to be 7 halves. That's going to give me 2 sevenths, u to the 7 halves. Add 1 to that, we're going to be at 5 over 2. So that means I got to multiply by 2 fifths. That'll make this 4 fifths, u to the 5 halves. 1 half, add 1, that will be 3 halves. So that will give me 2/3 u to the 3 halves. Don't forget your plus c that you require when they're indefinite, meaning there's no bounds. And then, last but not least, switch back so you have x's in your answer. Everywhere you see a u, you're going to replace it with, if you look up here, u is equal to x minus 1. I just go down here and I rewrite this as 2 sevenths x minus 1 to the 7 halves plus 4 fifths x minus 1 to the 5 halves plus 2/3 x minus 1 to the 5 halves plus c. And as we look at that one, I think you'd agree that without our knowledge of this substitution technique, there's no way we're getting that answer just by inspection. We have to understand how to use that process that I just showed you called substitution. All right, so hopefully things didn't jump too quickly for you there, but that's kind of the life of integration. This stuff ratchets up pretty quickly, and kind of our strategy is I kind of throw all of the techniques at you so you've got them at your disposal, and then we're going to spend 2 weeks. I'll throw you some intervals. I'll throw you a mixture of intervals, and you're going to just integrate and hopefully get better and better at this. It will be slow. It will be a challenge in the beginning. You have to put some time into it. And I know maybe under this current conditions that can be difficult, but it's the only way you're going to work your way through and become somewhat competent in these techniques. All right, here we go again. This one is a definite interval, so it's got bounds on it. I'm going to show you the series of look at both methods. I'll show you 2 things you can do. It doesn't really make any difference. They're both pretty much the same. Well, the first thing I'm going to do is I'm just going to pretend they're not there. And I'm going to try and look at this. This one you could probably do with just inspection, because if this was your u, the du would be 3x squared. The only thing you're missing for it to be u to the power du is your 3. And again, I don't want you to lose sight of you can do these very quickly sometimes. Please do them that way if you can. However, just because I'm trying to show you this new strategy, I will do it with substitution. I would never use this substitution unless I was just trying to explain how substitution works. I'm going to let u equal x to the 3rd plus 1. Reason being because I know the derivative of that is going to generate this x squared, which I'll be able to help with my substitution. Du is 3x squared times dx. Remember, instead of the dx going here, I'm just going to always tack it over here now. And now let's get this ready for our substitution. So to get x squared dx, I'm going to put du over 3. That's equal to x squared dx. And again, notice I'm just ignoring the bounds on my intervals altogether at this point. I'm going to rebuild the question with my new variable. X squared dx is your du over 3, so 1/3 du. Probably should be doing this at the end just so you have enough room to fill in whatever you need here. But in here, I'm going to need now this, which is u to the 1/2. Anti-differentiate. So I'm going to add 1 to the exponent, which will take me to 3/2. I'm going to multiply then by 2/3. So that's going to give me 2/9 because there's already a 1/3 here. U to 3/2 plus c. Now, this is what I mean by you got 2 options. What you can do is you can take over here and say if u equals x cubed plus 1, you can just stay with the letter u and you can switch your bounds from, these are bounds on the letter x. So what you can do is say, well, what would u be when x is 0? So you just say, well, what if x is 0? Then u would be 0 cubed plus 1. Then u would be 1. So instead of having x is 0, it's the same as having, what am I doing here? Sorry, it shouldn't be a plus c in this one because you've got bounds. So here, you can then put bounds on here and say instead of 0, you could go to 1. Then you got to do the same for the top bound. So say, well, what if x was 2? What would be the variable u equal to at that point? So then you would say u would equal 2 cubed plus 1. U would equal 9. So now you never switch back to your x's. You just substitute u is 9 minus what you get when u is 1. The other way to do it is when you get to here, which to be honest with you, I kind of prefer myself. I just switch back to the x's, 2/9. Instead of u, put x cubed plus 1 to the 3/2. Put your original bounds back in, and away you go from there. It's really the same thing. All you're doing is filling the numbers in within here versus filling them out separately here and then putting them in here. It's again, it's the exact same thing. So whichever you're more comfortable with makes no difference whatsoever. Let's continue with this one just because we have done quite a bit into it. So the answer now would be 2/9. So that constant, I'm just going to pull out front. U, so 9 to the 3 halves minus 1 to the 3 halves. And we have 2/9 fraction exponents. Remember, the bottom number is what root you're going to take, then you're going to raise it to that exponent. So this is telling you to take the square root of 9 and then cube it. Well, the square root of 9 is 3. 3 cubed is 9. 1 to any exponent is always 1. This will be 9 minus 1 is 8 times 2. The answer for this one will be 16/9. Nice thing about one like this is, I don't know if I still have it open. Give me a second. All right, so I just got Desmos opened up and ready for us here. So just to remind you that if you have a definite interval, you can always check your answer. So I'm just going to show you how you would do that. You go to Desmos. So I have it open up here now. And you're going to use your keypad down here. To get the interval sign, you go over to Functions. Under Miscellaneous, you've got your interval sign. So our lower bound was 0. Our upper bound was 2. We then had x squared squared, and I have square root of x subtract 2, and then the dx. Now make sure your dx is always out at the end by itself. Dx. Why did that not work? 0 to 2 squared. Oh, sorry, I typed it in wrong. That's why. X squared. This should be x cubed. Tells me that one actually didn't work. X cubed. X cubed plus 1. Oh, that's better. And I think, see here, this little button tells you that I'd rather have the fraction version of that. 52/9, which is not what I had. What did I do wrong? I typed that wrong. Let's double check. 0 to 2 x squared, square root of x cubed plus 1. And, oh, I know why right here. This should have been 27. That's why I missed having you guys fix all my mistakes for me. So this one should have given us, we said it was the square root of 9 cubed. And the square root of 9 cubed is not 9, it's 27. And 27 minus 1 is 26 times 2 is 52. Now, if we double check that and cross-reference, there we go, 52/9. And again, that just switches back and forth, fraction to decimal, whichever version you prefer. So it is a neat way to check your answer when you have a definite interval. All right, back here. Let's see what else I've got. I got a couple more. Okay, let's have a look at this one. Well, again, more from just having experience of doing these. Probably our best option here is if we let u equal the natural log of x. Now you say, well, why did you pick that? The reason I pick it is because I know before I even write it down, the derivative of ln of x is 1/x dx. And I notice here that I've got a 1/x dx. So du is 1/x dx. Well, so this part right here, dx over x, that's the same as 1 over x dx. I'm going to put du in its place. This is 5 plus u cubed. So integral, I'm just going to leave these out for a second. Integral of 5 plus u cubed, and that's in brackets, dx over x, that's du. Do not put these bounds on here because those are bounds on the letter x. I'm now working with the letter u, so those two bounds really don't apply if you're using the letter u. So that's why I just leave them completely out for now. So now I'm just going to do the integral of this, which should be easy to do. So it's 5u plus 1/4, that's bad for 1/4 u to the fourth, between, so again, you got the option here. You can say if u is equal to e to the sixth, sorry, not if u, if x is equal e to the sixth, these are on x, what would u equal? U would equal the natural log of e to the sixth. Well, good news is, I'm sure you all remember from grade 11, your properties of logarithms. If you have the log of something to any exponent, and the base of your logarithm is the same as this, the answer is just your exponent. That's a property of logs. It's important that you know. Hopefully you remember. Well, you look here and say, well, how's that apply here? ln, natural log, is shorthand for log base e. These are the same. This is just saying that u equals 6. If x was equal to e to the negative 6, then u would equal the natural log of e to the negative 6. This is base e, this is base e, u equals negative 6. So this question now is bound between negative 6 and 6. Substitute your numbers. 5 times 6 plus 1/4, 6 to the fourth. There's your upper minus your lower. 5 times negative 6 plus 1/4, negative 6 to the fourth. Well, one good thing I can see here is that 1/4, 6 to the fourth, and 1/4, negative 6 to the fourth is going to be the same as 6 to the fourth. So this answer and this answer are going to be the same. And this negative then is going to wipe those out. So really all I got to deal with, I was trying to do this using a calculator, is just deal with these two, because that's it. This and this will wipe each other out. Because of the even exponent on the negative base, you'll get the same thing. So you've got 30 minus a minus 30. Our answer's got to be 60 for that interval. And I'm not going to go through typing that one into decimals, but you could go and check it. Hopefully I haven't screwed it up. You guys will hopefully find my mistake if I have. But that's generally what the strategy should look like. And I got one more. So if I had this one, and I wanted to do a substitution, I think I would probably go with let u equal x minus 2. So now du simply becomes dx, because the derivative of the right side is just a 1. I'll go over here to rebuild this. I'm going to need something to put in there for x. I'm going to rearrange this. So x would equal u plus 2. And now the question gets reconstructed to be u plus 2. There's x squared plus 1 times u to the half dx. So I'm going to have to expand this out and clean things up here as best I can. Square the first, multiply and double, square that one, add 1, multiply by u to the half. Oh, that's du, not dx. Again, I need your help so I don't screw that stuff up. And then I'm going to distribute, like we did in one earlier example, the u to the half into each of these. And it will be u to the, so this is 4 over 2 multiplied by 1 over 2. So you add the exponents, it's 5 halves. Plus 4u, this will be to the 2 over 2, add 1 over 2, 3 over 2. 4 plus 1 is really just a 5 times u to the half, so that'll be plus 5u to the half. And then I've got my du at the end. So now I just have 3 power rules to undo. So anytime I can manage to turn what I had in the beginning into a series of terms added, subtracted, raised to numerical exponents, you have accomplished your goal of simplifying things. Add 1, you're going to be at 7 halves. Oops, I don't want it anymore. I'm going to do the antiderivative now. So it's going to be 2 sevenths u to the 7 halves plus, what have I done wrong? This should be 3 halves, not 3 over 2. So this is going to become 5 halves. So I'm going to multiply by 2 fifths. That'll give me 8 fifths u to the 5 halves. Add 1 to this exponent, I'm going to get 3 halves. So I'm going to multiply by 2 thirds. I'll make this 10 thirds u to the 3 halves. This one was indefinite, had no bounds on it, so it will be a plus c. And then finally, just switch back to your x's. So u is going to get replaced with x minus 2. So my final answer will be, that final answer will be 2 sevenths x minus 2 to the 7 halves plus 8 fifths x minus 2 to the 7 halves plus 10 thirds x minus 2 to the 3 halves plus any generic constant c. And that is a look at how the first technique of integration works. That's using what's called the substitution method. The only thing I can tell you is there will be a challenge in the beginning. If you try 1 or 2 of these and give up, you're setting yourself up for a long old process here because, as I said, integration is it's a slugfest in the beginning, and hopefully you can be persistent and work your way through it. Please ask questions. Again, I'll go through examples with you. We can video chat about them. We can do a live video chat and do a Q&A, question and answer. If we get a group of students that want to do something like that, we'll do whatever we can to try and work through these to help you folks get your head wrapped around them. So in your class notebooks, you will find these smart files that go with this, and you will also find a set of practice questions with an answer key tacked in behind them. They are borrowed from a college called Vanier College, which has some great resources out there that they put on the internet. So good questions with the answers all there for you. All right, so best of luck with the practice questions.